We have spoken about non-existence of limits in previous videos. Next we want to discuss the case where limits do exist, but the graphs of the functions exhibit some features that we would like to distinguish. And the concept that will be used over here is the concept of continuity. And continuity can be found in section 1.4. So let me illustrate the things that I'd like to discuss by making some graphs. So the first one is a graph of function sine of x. Now you know how it looks like. It's quite easy. Goes up and down. The next one is the following function, just an imaginary function, which looks like the following. So the function value is 1 everywhere except at 0, that's 2. Now the last example is sort of more realistic example. It has a slightly different behavior. So what we do is look at we're at September 1 on 0 degrees longitude, and our time is just before midnight. Okay, and we want to know what the number of the days. So we are still at September 1. So on our x-axis we depict the number of degrees longitude, and the y-axis is just the day, the number of the day. So at 0 degrees we are still on September 1, but it's a little bit to the east we are on September 2. When we go to the west, we are still at September 1, and when we go to the east, we are at September 2, and say the maximum amount we can go to the east is to 180 degrees longitude. And the maximum we can go to the left is 180 degrees longitude to the west. So we depict this as minus 180 degrees. Now let's assume that at 180 degrees eastwards we are at September 2, and westwards we are at September 1, but of course they are in fact the same positions on the globe. Okay. Now, there's an essentially different behavior for each of these functions. In sine of x, for instance, when we look at the point x equals pi over 2, no matter how you walk along the x-axis to this point, the function value has a limit, and the limit is equal to the value of the function at that point. However, if you walk to the point 0 along the x-axis, then you see very different behavior. The function makes some jump, and this is in both these cases, but of course there's still some more to be said. Let me first give you the definition of continuity. Definition 4 on page 78. And since we look at points, we call A our point of interest. So A is given, and we assume that the function is defined around this point A, otherwise we cannot speak about limits at all. So f is defined on some interval containing A. So let us call this interval A minus epsilon, A plus epsilon. So a little small interval around A of radius epsilon. Now we call f continuous at the point A if the following holds. If the limit when we walk along the x-axis to this point A, and we look what happens to the function value, then this function value has the limit equal to the value of the function at A. and we call f discontinuous if this is not true. Now, when is it not true? We have to look at the negation of the statement. Well, two cases. Either, case 1, the limit when we walk along the x-axis to the point A, then the limiting function value, the function value has no limit. Or, well, of course the limit can exist, but it's simply not equal to the function value at A. So the limit exists. Okay, so it's interesting to look at our examples, but then we have to specify what is our point of interest. So in the first, for instance, we take pi over 2, and what you see is that the function simply is continuous there. We walk to this point along the x-axis, and the function value simply becomes more and more like the value of the function pi over 2, which is equal to 1 here. Now the second case, of course, is slightly different. Our point of interest here is, of course, A0. In the other values of A, possible values of A, it's not interesting what happens at all. It's simply continuous. But in A0, something weird happens. So when we come from right or left, clearly our function value is 1, so the limit equals 1, but this is not equal to the value of the function at 0. So we are in case 2. Discontinuity case 2. Now the third example, something even more weird happens. Whenever we walk to 0, so we look again at the point A equals 0. Well, there's no limit. So we have a discontinuity case. And which discontinuity case do we have here? It's case 1. Now, of course, there is some sort of, it's not too bad. When we come from the left, then clearly the function has value 1, and the limit is 1, and it's equal to the value of the function at that point. So if we only restrict to coming from the left, we have some sort of continuity. The jump that happens is when we come from the right. So in this sense, there is some nice behavior, and this is the concept of right and left continuity. So in this case, you can imagine that when we come from the left, the function value, the limit of the function value is the value of function at 0. This is in fact the case of left continuous function at 0. Now, you can imagine that when we would swap how right continuity should be defined. So you can look at definition 5 of the book in the same section 1.4, where right and left continuity are discussed. You have to look it up. And of course, then you also have to look at definitions of 6 and 7, where just the concept of continuity of a function is discussed. So not only at a point, but at a whole interval of points. Now, I will not go into many more details. What I'd like to emphasize is that most functions that you will encounter are either continuous or, well, they have jumps, like this one. And the typical sort of functions having jumps are related to probabilities. So let me give you an example, because you will encounter this in your probabilistic and statistical courses. So we are going to throw a coin. It's a coin which is not biased, so an unbiased coin, and this means that the probability of heads is the probability of tails, and this is equal to 1/2. What happens when heads comes up? We get 1, and when tails comes up, we get 0. Now, of course, this is not a function. We associate with these probabilities, we associate the so-called distribution function. It is denoted by capital F of x. And what does it mean? It's the probability that we get less or equal to x. How does this function look like? So if we vary x, let me give a picture. Of course, it's a probability, so the values are always between 1 and 0. Don't make the mistakes that you get negative probabilities, as some students tend to do, or probabilities greater than 1. Now, let me draw it. What happens if x is smaller than 0? Well, we get either 0 or 1. Probability that we get less or equal to -1 is 0. Because it simply doesn't occur. So this function is equal to 0 on the negative x-axis. What happens at 0? Well, then we have to calculate the probability that we get less or equal to 0. Well, this is of course the probability that tails comes up, which is 1/2. So at 0 we are at 1/2. What is the probability that we get less or equal to 1/4 or 3/4? Well, this is just, we cannot get 3/4. This is the same to the probability of getting less or equal to 0, because we cannot get anything between 0 and 1. So this probability is equal to 1/2. And finally, what is the probability that we get less or equal to 1? Well, we get 1 if heads, 0 if tails, so this is always happens. We cannot get more than 1, so this has probability 1. It's very good if you just study this carefully. Now, what's the probability that we get less or equal to 2 or 1 million or whatever? It's always 1, because we get at most 1. So this function has this shape. You see that we have jumps of the same type, only there's a difference. If we now come from the right, then the function value becomes closer and closer to the value of the function at this jump points. So that's, I already draw it as a sort of right continuous function. If we come from the left, then of course if you get closer and closer to 1, then you just make a jump at 1, so it's not left continuous. This is a typical feature of distribution functions. Distribution functions are right continuous. And what you also see, because you compute probabilities that you are less or equal, that you get less or equal to x, it must be increased. This probability increases as you increase x. In fact, it would be more precise to say that it does not decrease.